deck for thinking it's going to be an hour.
Uh-oh.
And suddenly realizing what's happening. So the deck is like Richard told, like encyclopedia. I try to condense it. I speak really fast. It's going to be a bit of a dive. How many here are familiar with Spark? Oh, this is awesome. So let me just jump right in. Right? It's not much about ad analytics. We're pretty naive in that space, but we are working with customers who are doing ad analytics, so you see some flavoring for that use case. So a bit of a pedigree, I think it's kind of we're going to cover. We are spin out out of Pivotal. So we essentially built Gemfire with the co-founders of Gemfire, built it over a decade within Gemstone, then within VMware, and then we're running Pivotal. So it's a lot of what we are doing is based on the lessons of essentially building an OLTP-centric database, making it run on top of Hadoop, and lo and behold, everybody said, hey, you know what, I need to run my query on top of this thing. And for those of you who know how OLTP database is designed, it's a OLTP database, you really need problem orientation, you run into all sorts of challenges, it doesn't work. And really, where we see this going, I mean, and you see this with SAP HANA, somebody mentioned, you see with Hackathon, you see with BBQ Blue, that you're slowly seeing that while you've seen the OLTP databases, then you saw OLAP, it's going to be a fusion of these databases, right? Essentially, it's going to be one database that offers both, not for all workloads, but that's where it's going, right? So we tried to do that similar thing. We took the Gemfire, essentially, technology, and we're deeply fusing it with Spark. So in a way, our mission really, we developed it for about, say, 8 months or so inside Pivotal. We got spun out on 1/1. So really, it's funded by Pivotal, funded by GE, and we have a third investor. So it's a 8-month-old startup. But the team itself has been doing this thing for roughly a decade or so. So that's us. So I'll just jump right in. So the way it is organized is that I sort of touch on what we think is complex in Lambda. Everybody knows Lambda, right? Then I go into sort of what's going on with Spark 2.0. Then I still point out sort of the challenges even within the Spark environment, right? Especially when you're trying to operate at high speed with modest costs with infrastructure, what kinds of things you're running into. And then touch on sort of how we are doing the fusion to some degree. And then I touch on sort of this fairly innovative thing that's been in academics for a while, the whole field of approximate query processing. So incorporating what's called as a synopsis data engine inside, if you may, this OLTP plus OLAP database, the role of column database all in memory. So focus is all main memory. So
this is not AWS Lambda, right? This is what Lambda is.
Well, I'm just touching on saying Lambda architecture, which is the pervasive way by which everybody is building big data architectures today.
Like AWS.
AWS is an example of a Lambda service.
Serverless.
I mean, the Lambda will touch on that essentially. So the idea behind Lambda is that can there be an architecture that allows not only insight gathering from a batch perspective, but how can I essentially use it in a real-time context, and how can an application bring the insights that you gain in batch and real-time together? Right? But the problem with this architecture is that you're taking data and essentially shoving it across a whole range of products. Right? First, you're taking a new data, pumping it to HDFS as raw data, you're taking that same data, sending it across to Storm, maybe Spark streaming, going through speed layer that in turn has to work with essentially some NoSQL, Redis, Gemfire like database, like a OLTP database. Then you have a serving layer that if you look at sort of Nathan Mars, the guy who kind of came up with the Lambda, he talks about a different DB, and then you have the application is left with the complexity of bringing these views together, which in the real world is rather very, very difficult, especially if you care about consistency. Right? So to us, Lambda architecture is rather complex. You have to learn and master multiple products. It's just giving you a high level of what might be going on in the Lambda architecture, especially from an efficiency standpoint. It is slower and you waste resources. So one of the things is that you see a lot of what I'm going to talk about touches on some of the performance as a metric by which we are doing things. But we see that for a lot of workloads, performance, if it's not good, you land up adding more and more complexity because you're increasing the cost of running an infrastructure that is rather large, and in any distributed system, you increase that capacity, increase the size of a distributed cluster, the more are going to be the likely problems that you run into, especially once it's in production. So, the mission BDAM is saying, can we simplify and optimize? Can there be a single cluster database that can manage stream state, transaction data, and run OLAP queries? We made a big bet on Spark. It's all centered, focused on Spark. So it's all about Spark APIs. But we're sort of changing Spark from being a computational layer to literally being a database itself, right? So it's Spark++, think about it. It's completely compatible with Spark++, so that multiple users, multiple apps can come and run their queries, run their jobs concurrently, run transaction operations on the dataset also concurrently. We're not trying to sort of aim for the whole world. In other words, this is not really designed for saying, bring me a petabyte data and work with it, focused on operational use cases. So let's just quickly go a simple example with ad analytics. So here what we're talking about here is, you assume that there's an ad serving company that is essentially running ad servers. It's hosted, it's really serving a whole bunch of websites. You get impressions coming in, and you get sort of click streams. The click streams are then turned into impression logs, right? An ad impression is every time you see an ad, it counts as an impression, not a click-through, right? That's the difference. Which basically implies that, millions and millions of ad impression log messages are coming essentially into this cluster, right? So you obviously want to front, this is like the simplest view into a Lambda architecture, right? So Kafka queue is being essentially sucking up all the events, and then going into a Spark streaming cluster. So the Spark streaming cluster is doing micro batching, which we actually believe is a better approach than the event at a time for a whole range of scenarios, right? In fact, that's one of the lessons learned, that we did a lot of things around event at a time, extreme low latency, like for algorithmic trading and stuff like that. But realistically, that thing that says a second latency is good enough as long as you can make it predictable and you can essentially stick to the constraint, really works really well. So we're big fans of essentially that approach that says, listen, when the data comes into the stream, you can split it into my batches. And the other beautiful thing with Spark is that it has this whole notion of lineage that some of you guys understand, which basically means even when I'm processing it in main memory and I'm running it through a whole bunch of transformations, I don't have to really replicate the data set. Something goes wrong, I can go back and replay as long as I know my constraint in terms of how much I can tolerate, right, in terms of the delays. So anyway, so this is sort of, and then you're saying, as it's getting processed, I'm writing it to a fast database, and I'm also writing to HDFS, through which then I'm accessing it through a SQL layer on top of HDFS, right? And the app essentially has to deal with essentially both these tiers, which means that the app has to think about consistency, right? Because you essentially have the fresh data sitting here, and your historical data sitting and being exposed to something on top of Hadoop, and they don't necessarily sync up, right? Because you can have duplicates going around across the two, right? So, what we're trying to do here, I don't go into too much into the program. I don't have the time because I'm going to show you guys the real code examples and all that in this thing. But we just it's a very simple sort of schema that says, hey, the input is really timestamp, publisher, advertiser, geographies, the current bid price for a particular ad, and the cookie in case you want to sort of do tracking of users. And given the flurry, the rate at which stuff is coming in, you want to condense, you want to sort of pre-aggregate it. Right? So what we're doing here is to say, can I aggregate this logs by publisher and geography, and then putting it in main memory, right? So essentially, I'm constructing a log message or an aggregation message per geography, per publisher, per ad, once a minute, right? That's okay. Even then, it's building up pretty significantly, very quickly, right? So essentially, the aggregated stuff looks like you have publisher geography, and then we're aggregating and saying what's the average bit for that 1 minute interval, and we're also computing the number of unique visitors that we saw in every minute interval, right? On which I can run analytics.
Sir, question here.
Yes, sir.
You aggregated, but do you also store this somewhere?
Absolutely, absolutely. It's going to the in-memory store. Obviously, will also flow into a back-end storage system, right? So this is how many of you look at Spark put it up? Some of the things have obviously changed in Spark from. RDD is old news, right? Everybody started talking about RDDs, and that's how people think about Spark. No longer, RDDs are really sort of old news. Everything is based on data frames, and that is a single abstraction that crosses all the Spark layers. So what this is showing is based on what is called a structured streaming. That is a new paradigm in Spark for how streaming happens. So the idea here is that, I mean, those of you who don't know Spark, I mean, the code will read saying, the first line says, hey, start reading micro batches in parallel from Kafka. And it's smart enough to know, Spark is smart enough to sort of understand the partitioning in Kafka so that it sticks to the same partition so they get heavy throughput, right? And the next sort of single line there is simply saying, so what happens here is that the Kafka stream is continuously emitting data frames, right? It's a data frame that comes up. And then essentially you run it through this next line, which is simply says, like, it can be done in SQL also, right? And it's basically saying that you filter and collect events every minute, reduce it down to 1 minute per population in geography, right? And again, this statement, which is doing aggregation, is again emitting a data frame. Except nice thing in our Spark streaming is that you can essentially introduce window clauses. So you can do streaming windows on your data set very easily and nicely. So all this can also be done in SQL. That's one of the additions we added. So if you want to come in from an external client and essentially register what is called as continuous queries, you can do that too. And then finally, what you plan on doing is, hey, I pre-aggregated a normal scenario, write it to Cassandra, to Redis, Gem, or what have you. So you're essentially doing the thing that says, hey, take the result, which is a data frame, and simply write it out. So everything, if you notice, everything happens in batches, right? And not only that, everything happens across all partitions in parallel, so you get a dramatic, very good throughput. That being said, I mean, there are still bottlenecks, right? This is what I'm highlighting here. I mean, those of you who operated and run any Spark program, the moment you go beyond the hello world, you would run into this thing. The first thing you would run into is the cost of what is called as a shuffle operation, right? A shuffle really is anytime I do a join, it requires a full shuffle. Anytime I do a group by, it involves a shuffle, map reduces a shuffle, right? Essentially, it's like saying I'm moving massive quantities of data across the network, essentially to do my job, right? And all of a sudden, everything starts to slow down. And the next thing is that, hey, we landed up now taking after shuffling, we created a new batch here, and you're writing it back out into Cassandra, which again is a shuffle. Not only am I serializing it into Cassandra, you again are doing a massive shuffle operation, you're doing data format changes, you're incur serialization costs also, right? It's kind of what I'm highlighting here. I mean, you see it all over Spark literature, right? That Spark breaks down any given computation. In this case, if you look at even this query, it's really broken down and it starts to look like this at runtime, right? So a bunch of stages. Each stage essentially is running concurrent tasks in parallel across a bunch of machines. And so you one guy is continuously writing. If it's a group by, the other guy is continuously reading. Pretty expensive, right? Larger the data, more expensive it is.
Question?
Yes.
On your previous slide, you said the shuffle is expensive. Is that, did you find it to be expensive because it shouldn't be for that particular thing?
Yeah, it would be, right? I mean, if you were to assume saying, I mean, it's all relative, right? Now, assume saying that the input rate was 1 million a second, right? And assume saying I didn't go a minute, I started doing it every few seconds, right? Then all of a sudden, even if it was a minute, and let's say I reduce it, maybe 1 million got reduced to, who knows what, maybe 500,000 or 250,000, right? So it's all relative. Yeah, I mean, when I say geo, it could be, right now my example is a state, but it can be much smaller. So I don't take it for this example isn't really a lot of data, but you can imagine scenarios where it can be a lot. But as you see, it's not just the streaming scenario, but also the scenarios where this becomes the biggest problem. The other thing I think I'm sort of highlighting, people sort of tacitly know this, but people tend to forget that, I mean, to me, it's literally you avoid the shuffle and you avoid the costs associated with copying and recopying. I mean, that itself gives you such dramatic savings. It's amazing, right? So I'm just highlighting what would happen if you were to simply take a piece of data and simply replicate it in this modern Java-based systems. The number of copies that it goes through, right? So you're essentially looking at a copy inside a Spark layer, going from Spark or network buffer to the kernel copy to the user space inside of, essentially, something coming in, the young generation, the from to the older generation. And let's say if I replicate, again, I have to do the same thing on the replica, and then an act comes back. So you land up making about 8 copies of the data, right? If not more.
That's a nice example.
All right, so the next thing is that, hey, listen, not only am I now streaming, processing my data as it's coming in, I'm pre-aggregating, I'm storing it. And what is the next thing I want to do? I want to ask insightful questions, right? Another insightful, I mean, this is a simple example. It's saying, hey, how do I ask analytical questions? Every analytical question turns out it's a scan-oriented aggregation class question, right? In other words, if you look at a question that says, find me total uniques for ads, group, and geography, that simple question requires me to literally scan through every single record all of a sudden, right? And that becomes the single biggest, I mean, if you start running a Spark streaming cluster, I mean, a 2-node cluster can handle about 2 million a second, right? If you don't do any of this expensive work, I mean, you stick it into the same partition coming in, stick it into a, let's say, memory database where the partitions are co-located with where Spark is partitioning it. You got 2 million a second with just about 16 cores volume, right? The moment you do a query like this, bam, it's sucked up all the CPU, right? And all of a sudden your streaming starts to throttle, everything starts to look bad. But anyway, so the point here is that, hey, you're doing a scan-oriented query, right? And what is the alternatives? Well, I'm either storing or sticking my data into a row store, a Cassandra, or I'm sticking it into a column store, right? Well, it turns out, I mean, these row-oriented databases are great at fast key-based lookups, right? Of course, they're slow in aggregations, and there's, scan-based interactive queries, and of course, they consume too much memory because given a key, I should be able to look up something really fast. That's the design center, but it really consumes a lot more memory. A column-oriented database is great at doing scans, aggregations, but updates and random writes are relatively difficult in a lot of the older, especially MPP databases. Right? So this is a favorite slide of mine. I show it because it highlights what most people maybe know. The fact that, I mean, today you see that, you think that, hey, I can put it in memory and I'm going to go at really high speeds. I mean, just the experience we got when we said, hey, there's a memory database, and will it go really fast? Truth is that it won't, right? And the reason is that, I mean, if you just scatter your data across memory, and if I'm doing a scan, I mean, my CPU is constantly jumping across different memory locations, right? And if you look at a modern day CPU, I mean, it's all designed to say, how can I make use of the CPU registers, the L1, L2, and L3 really well? So it's all about sequential data. If you work on sequential data, you get dramatic. You get 3 orders of magnitude performance difference, right? Just do a simple experiment. Stick something in a million things inside a hash map, then stick a million things inside an array and compute an average. You see that there's a 3 orders of magnitude performance difference. So that's the point. I mean, so if you were to go back to the 80s, it took about 6 clock cycles for a memory round trip, right, from the CPU. Today, actually, it takes a whopping, I mean, it's not even 150. Sometimes it actually can take 300 clock cycles. So you just fetch an integer out of memory, right? Because the speeds at which DRAM have taken off, there's a huge delta. So in some sense for us, the hardware changes have sort of manifested this thinking that says memory is the new wall. Right? I'm actually going to go beyond that in a second. All right, so how does Spark do? In Spark, so this is the idea of Spark, right? I mean, Spark, if you cache, if you persist, it actually turns, Spark, everything is immutable. Right? I mean, Spark by default says, bring me your data, we can change anything. You bring me my data, I'm going to stick it essentially in what looks like arrays. Great, it's all sequentially organized the way it needs to be organized for analytical processing. But ironically, it doesn't Spark at all. I mean, it sticks it in with a query engine, which is a catalyst engine, says, give me the next little, I'm computing an average, the next little integer, but it turns it back out into like a row and then offers it to the next layer. All of a sudden, you've lost that ability to essentially operate in a sequence fast enough. Right? And hence, it was kind of slow. But Spark made a big difference. All the right changes have started to emerge in terms of what you would hear essentially as vectorization. Right? Essentially, how do I do array-based processing? How to do processing so that I can operate at the speeds at which CPUs can operate. So, in a simple example, I'm essentially operating over 105 million records on my laptop, an average bid over all my ad impressions. If I'm going from arcades and voice buffers for 3 seconds, 600 milliseconds, good, but is it good enough, right?
Question?
Yeah.
Don't you anywhere reference to tungsten?
Yeah. So yes, I mean, it doesn't really matter, right? I mean, tungsten, what tungsten was to say, hey, I don't want to like overstress the garbage collector in the JVM. So there's an ability to say I can manage off-heat. But that is orthogonal to the fact that how exactly did I organize data in main memory, and how did I access that in my query engine from main memory, and that's where the...
But you get the benefit of the
but is it really, really good enough, right? I mean, that's the question, right? Because remember, I mean, the world we're living in, I mean, we're constantly operating on billions and billions of things, and constantly asking questions that require you to operate on billions of things to give you an answer, right? So that's why all these things start to matter, right? Ultimately, it has a cost implication. That's the other big thing I find. So anyway, so if you look at, I mean, the Spark prototype plan, the Spark UI, I mean, you start seeing things like this now, right? I mean, this is simply a plan, a physical plan for what happens for a select average from a table. And yeah, I mean, essentially, you start seeing this thing called goal stage code generation. It's a big touted thing in Spark prototype. So the point here is the following. In Spark, before Spark prototype, it was all about somewhat inefficient way of working with columns. And now essentially they're turning it into native code as the queries start to run, right? I mean, it's sort of a, just put it out there, the famous adage that says, you want to remove complexity, then why don't you add a layer? But if you want to improve performance, what do you do? Remove a layer, right? So that's essentially the kind of thing they did in some sense. So typical query engine design, if you look at this, right? I mean, if you look at the query, you did a scan, a filter, and an aggregate and a project, right? That was the mapping of that query. And in any typical query engine design, what would happen is that each operator, a scan, a filter, would be implemented using functions. And the moment you have functions, it's like saying the CPU is constantly chasing pointers, it's going everywhere in memory, all of a sudden it's slow, right? That is what was going on before. Now essentially on the fly, we generate code. It amounts to saying I can remove all sorts of virtual function calls. And if you give me an array of memory, I will essentially, almost like machine-generated code that just walks to the memory, binds it to the CPU, and yeah, that's it. Your CPU code completely be bogged down. Right? I mean, the idea is to sort of capitalize on the modern-day CPU design and cache. Right?
I mean, in a way, Vaxxon were honest about borrowing atomic instructions, and now Intel is prefetch. So you really want to stay in the CPU.
Yeah. I mean, it's a tricky balance, right? But you're right. I mean, it's to a great extent when you're doing analytics, it's a throughput-bound problem. Right? You want to like give an end course, am I completely pegged at all cores at all times? Oh boy, I mean, I'm way off on time. Right? I'll just keep skipping fast. Okay, so is it good enough? Well, no. You're hitting the CPU wall now. I know that's sort of a term very why? Because how often do you run queries like this? I mean, it's great to run an average. Give me this, bam, and you're going to get actually 600 milliseconds. Is it'll actually go much faster. I mean, on my laptop, I was just using 2 cores, actually just 1 core. Start using more cores, it'll be significantly better. But that's all great. But what happens in real life is you're running queries. This is actually a simple query, right? I'm doing a 3-way join, natural join, and I'm doing a group by, and I'm doing an ordering. Well, guess what? What happens? I mean, if you run that single query, I mean, this is on my laptop. I don't remember how many concurrent tasks I had, but it takes a whopping some 60 seconds now to do this, right? You went from something that took 600 milliseconds, I iterated over 105 million things, and I all of a sudden went to about 60 seconds. One user, it's only one user, and I pegged all my CPUs, right? And then now if I put 10 concurrent users, right, 10 concurrent guys essentially running the same query, it's a whopping 200 seconds to just return an answer for such a relatively very simple query. My record count is only 100 million things, right? So the point is that in-memory analytics is great, but it's not panacea, right? Larger volume, more concurrent users you have, more visual tools you throw at it, all of a sudden you need more and more infrastructure. And the truth is that DRAM is still expensive, right? I mean, it is following the Moore's law in terms of densities, the price is coming down per gigabyte, but still it's relatively expensive. Of course, the power consumption cost will just kill you if not the price of the DRAM itself. And then the other important thing we're seeing is that a lot of the guys are just saying, I want to run analytics in the cloud, right? I mean, what does that exactly mean? Because your data sets are inside a firewall. You want to just move the right data sets off into the cloud so that you can run analytics. And all of a sudden you figure out saying, well, even at 100 megabits per second, it takes about 24 hours to transfer 1 terabyte. Right? And that's why the moment you get to about 2 or 3 terabytes, you're better off actually literally taking disks and shipping it. That's what all the other e-commerce guys are doing, right? They're literally shipping disks. You know why? Because it's significantly faster and cheaper to simply ship physical videos, right? But is it really sustainable? That's the problem, right? To move such large volume. So, well, how about not working with large volumes at all? Right? How can we flip the big data problem to maybe a small data problem? Right? So that's where we're investing a good chunk of our energy also. Saying, can we use statistical techniques to shrink data, right? And what we mean by statistical techniques is you're building out a bunch of synopsis data structures. The easiest example is a sample, right? A uniform random sample. But we're doing more sophisticated sampling, like stratified sampling and things like that. I mean, how many of you guys have heard about BlinkDB? Okay, you have a couple of guys. Okay, sure. So, I mean, it has it's got some similar underpinnings in terms of the algorithms. It's vastly different in terms of how we've tried to do the SQL engine. But anyway, so it's a similar idea, right? Can I essentially take 1% of my data and still answer about 70% of the questions you'll ask? Oh, 5 minutes, okay. There's no way I can cover this. All right, I'll leave the slide deck out there and on the website, right? So the point behind this is that I can use some of these techniques for a number of use cases with significant reduction in the resources that you need and still answer analytical questions in a split second. Right? Don't spend 200 seconds. I can't give you 1,000 rows. Here is my laptop. Here is a database that is sitting there with terabyte of data. Can I run analytical questions? Give me an answer back in 1 second, and I can bother all the other guys who will also be running those splits. That kind of problem, right? And especially works well for like things where you're visualizing. Like look at this map plot, right? This is done in University of Michigan, right? They developed a thing which you're kind of also working on. I mean, this was plotted using Tableau, 2 million data points, 71 minutes. Done with an approximation scheme. Just took 3 seconds, right? And you can tell the visual icon tell the difference. Anyway, so Snappydata, I mean, it's a product club, right? Hybrid open source system for transactions, analytics, and streaming. It fused essentially. I mean, it's a fusion. It's not really an integration. It's a deep fusion of what we did for Jennifer, which is a low latency HA, high concurrent design with transactions, and Spark together. So here is so we go from what we think as saying, hey, what do we need a speed and a serving layer as isolated? Not for all use cases, some use cases where we can fuse it together, right? So what we've done essentially is that you take Spark streaming, the streams are coming in. Essentially what we do is we run our store in situ in process with Spark executors itself. Right? So what we do is we don't have to essentially copy, serialize, any cache data sets in Spark. We can essentially manifest them in our own tables. So you can come into Spark APIs, access it. We have extended the Spark API so that you can do transactions on the same data. I mean, there are a number of things we've done. I mean, I don't have the time to cover it, but some of the slides we'll talk through it. And then we incorporated the synopsis data as if it's like indexes on top of these tables. So you can leave the data sets in S3, essentially have Spark tables that point to S3 data sources, or you can essentially have tables that are really manifested as column tables or row tables instead of a product. Right? And the interfaces are like, hey, you can come through the Spark APIs, and of course you can come in through SQL. Right? I mean, this is sort of the little bit of the detail, and time to cover this. Yeah, so it's fast. I mean, there are a number of reasons why it's much faster than actually Spark. Even for Spark workload itself, we get a dramatic improvement. Even when you cache the data inside a Spark, you can actually because we also did doing a number of improvements to how they do vectorization itself. Right. And why is it flexible, and how do we work with the ecosystem of data sources? That's all Spark. I mean, that's just every vendor is sort of saying, including Apple. I mean, starting to probably work with Apple, right? As a storage.
And your vectorization is running into your own sense of using array very quickly from your own local indexes.
No, I mean, the vectorization in Spark is all based on array processing. What we landed up finding is that they only were supporting perimeter. I mean, if you look at Spark, there are Jira's open on this one. they're only doing a good job at primitive types. And the moment you go beyond primitive types, even for strings and stuff like that, it's not really done well. So we did a bunch of modifications. I'm not so familiar with all the modifications. And then, of course, we get a huge benefit because we can now co-locate data sets because we understand foreign key relationships and things like that. So we can immediately co-locate related data. So when you do a join, I don't even have to shuffle. I can immediately do a co-located join. Things like that. Yeah, I mean, I've covered that, HA, all that sort of stuff, right? So here is our current TPCH. I mean, sort of the benchmark on trying to find out how good you are with analytical queries. So we did with Spark comparison. This is open source, so you can download, try it out.
So Jags have been approximate results or accepted?
Try it out, that's why I said try it out. Right? So I'll just skip through this. Really, I mean, this is just again touching on the value of thinking about exact versus approximate. And the way we do it is that it's not like you just run a query and if you point to an approximate sample, in a sample you get an answer that's kind of incorrect. You gotta have a knob that allows you to say how correct do you want the answer to be. So you almost think about these approximate structures as if like they're indexes, right? So depending on your tolerance for errors. So let me see if I can go have like a few more minutes, 5 minutes. Yeah, I want to show the demo. Maybe that'll get it wrong.
Yeah, it's okay staying, sure.
Yeah? Alright, cool. Okay, so this is, the hello world of analytics, right? You work with the on-time performance data for all domestic airlines available from FAA, right? So I have like here's what I do. I mean, what I'm trying to show here is that, let me load the data, straight up Spark program. And then I'm loading it up into a column table in main memory, right? And then I create just one stratified sample. Then we look at how fast can the stratified sample answer be, and also how good can it be, the quality of the answer itself, right? So I'll have the left pin that's showing running the query in the full column table and running the query on the sample table, right? So the loading is just straightforward, right? I mean, point to folder. I just essentially, the data set actually in the folder is about 55 million. I just unit it about 4 times, I got about 210 million records. Then I create it's all straight up Spark, right? I mean, I create a data frame, register it as a table, right? Then I run my SQL that says I create my sample. I mean, there are some options here. I'm not going to get into that. I mean, this is essentially saying on which columns do you stratify on, what's the fraction of the sample. And then we do things like what's called as reservoirs. I mean, we essentially allow sampling to even work, even if the data is continuously streaming in. So sort of, you want to see that. It's where we also can create tables that are row-oriented tables. In this case, a replica table. I'm joining it constantly, so I'm going to replicate it. So here it is, right? I mean, you can see it. But I'm running this query on the base table. This is the full table, right? I mean, just the column table. 210 million records. Now, if you look at that, I'm running pretty much the exact same query, except I added a with error of 0.1. That's a constraint. I'm saying that if you tolerate. And all of a sudden it scales the answer to nearly, if you look at the answer, it's about 99.99% correct, right? Even though the actual count is about 2 million, right? I mean, here is the Spark console. We have our own extended tab in the Spark console that shows that, listen, if you look at the sample, it consumed about 105 megabytes. Even though the full table, we don't show it because we just cache it in Spark, it's about 7 gigabytes. So now let's just run some queries. I mean, which airline is the most flights. You see that the left query is running the full table. I ran it concurrently, several queries, right? And the right tables are all showing the sample queries. And you see that as I started running concurrently, sure it was on the laptop. All of a sudden it's like 107 seconds to do this thing. This took only 2 seconds, and visually you can't tell the difference. In fact, actually in this query, it's again 99.9% correct. Not that in all queries the answer is going to be 99. It depends completely on your data sets. So likewise, if you see this query, a similar pattern, right? I mean, and we have other options. For instance, so if you look at this data set, what we have, this thing. So one of the things we kind of have is this notion that says, listen, I mean, I want to do analytics, let's say Zeppelin for the matter, Tableau later on, things like that, or Zoom data, we're working with them too. To sort of say, I can provide a directive that says, it's okay, I want to see my results right away, right? I can immediately see my results, and then, and then on the background, you can start running your queries. If you look at this thing, you print it out saying a time code executable and sample took about 3 to 5 seconds, and then behind the scenes it runs the same query in the base table taking 87 seconds. Right? So the idea here is that I can keep just my samples, move things around, run my queries really efficiently, really fast, and then leave my data in S3 or whatever else. Just do that. Spark does a good job. Yeah?
Here that, say suppose you sample 5% of it, right? You got one result. Then you select me to 10% and see if there's any change in the result. If it's pretty much the same, you can say 10% is.
Absolutely. I mean, it really comes down to the budget. See, what would happen? I mean, we are actually working on what we call as a workload miner. So that you don't even have to think about what should I sample on, right? What we're working on is that we will understand workloads and basically mine workloads to understand data distribution characteristics, understand what kind of queries you typically run to figure out the samples you really need. And the best part of sampling is larger the data set, smaller the fraction that needs to be. That's the beauty of it. That's what I was trying to show with this slide. That this x-axis is actually not only time, but it's also the volume of data. And what you see is that the error rate essentially exponentially drops with the volume. Right? What that basically means is after a certain point, even if I double my sample, my error has only gone and changed by maybe 0.5%. Right? So that's the beauty of that thing. It says if I'm working with a billion objects, maybe my sample needs to be 20 million. If my data set was 5 billion, maybe I only need another 10 million. Right? So it's all math. It's very nice. Okay? Yeah, I was going to call all this project, sorry.
So you're using the same methods as BlinkDB for sampling?
No. So BlinkDB started also with essentially this notion of what's called as curated sampling. But they have shifted. First of all, the project is kind of idle for a while. Right? The committers have moved on to a few other things. But now they're taking essentially what's called the GOLA approach of doing online sampling. So it's the GOLA approach has pros when it comes to no matter what, give me an accurate enough answer because it essentially keeps on working with the real data set. Their approach is to say, sample and find out whether the error is within whatever percentage you have. If not, I'm going to keep on reading more and more. In our world, the samples are absolutely always sitting in main memory. So you get a huge performance boost working on curated samples. The disadvantage is that if the sample is not right, I cannot give you an answer. Right? So then you read. See, what we do is we automatically read out. We've done all this thing inside the Catalyst engine itself, which they haven't done at all. Right? BlinkDB essentially is not even a release project, by the way. So we've done it at the SQL layer, so that you just run the SQL queries, we figure out what to do, including when to run bootstrap, how to compute the errors, how to do sample selection, all that sort of stuff.
Do you have a weighted hyperlog or?
Yeah, so stratified sampling is one thing. I mean, we're looking at Bloom filters, hyperlog. We have a time series based confidence sketch thing. That's why we're generally calling it a synopsis data engine.
So what was the result of hyperlog?
Well, I mean, the stratified sample is significantly better in terms of what all questions you can have. The hyperlog you can only do a count distinct kind of question, right?
Yeah.
That's the thing. So
okay. Thank you.
They're
Thank you.
Thank you.
okay.
When do you plan to support joining?
Say that again.
When do you plan to support joining?
In the base product or the sampling technology? Pretty soon. So right now we do support it, except there are restrictions in whether you can do any sort of arbitrary distributed join or not. So today, for the most part, it's like saying if you did have a star schema or a snowflake schema, your fact tables, right, the huge tables can be samples, but other tables will have to be full data sets because they're typically very small. Right? So you don't support sample joining to other samples fully, except that when the cardinality is 1-to-1, we do support it.
Will you support?
Yes, we will support distributed joins. Yes, we will. Okay. So yeah, I mean, Because if it does, we're going to be late.
We're doing the same talk in LA and the Spark Summit, Spark Summit Meetup tomorrow.
Don't approximate your time.
Thanks a lot, guys.